Okay, so we're going to start looking at properties of radicals and radical functions. And so what this video is going to do is take you kind of on a whirlwind tour of all of the things that you know already about radicals. And then we're going to use those things, kind of expand on them, and talk about what's special about radical functions. Okay, so to start off, let's just define what a radical function is. All right, we're going to do some vocabulary, and then we're going to get into some of the properties. So to start off, a radical function is a function where the variable is underneath the radical symbol. So just so you can see kind of things that are and are not radical functions, we can't just assume that because there's a radical somewhere in the function that it is a radical function. So if you take a look at my first two examples here, we're saying that in both of these cases they are radical functions because if you notice, the input value x is underneath the radical symbol, right? So I have 2x and that's underneath my square root, okay, and we have a 4x and this is called a fifth root. We're going to discuss what that means in a second, right? But I have this other one, g of x, that I'm claiming is not a radical function because even though I have a radical right here, it doesn't have an x value underneath of it. I can actually just take the cube root of 8 and simplify that, and we would actually say that this is a linear function because the expression with the variable is outside of the radical itself. So just something to keep in mind. Don't assume just because you see a radical that it's going to be a radical function. If it's going to take on all these properties, that value really does need to be underneath the radical symbol. Okay, so let's talk about just some quick vocabulary before we get into our properties. And so a lot of them are going to revolve around this radical symbol. So everything that you've done up until now has really focused on square roots, right? So we've never seen this number right here sitting on the outside of the radical symbol, right? So the radical symbol is that little check mark symbol that we've been using for square roots, right? The thing that's underneath the radical we call a radicand, so that's something that we know. So we now have this new thing called an index number. And so what the index number does is it actually makes the radical mean something different if we change the number. So it's still the same concept, but we can change the idea slightly. So here's what it means. If we have an index of 2, right, that's a square root. That means what we've been using. We're saying multiply a number by itself, and that's what, if the radicand is equal to that, then we can take the square root. So as a simple example, I could say if I have the square root of 4, that the answer is 2 because 2 to the second power would give me back the 4, right? So if I were to take my answer to the square root problem and square it, I end up back with the radicand, right? And so usually we've never written this, but there's an index of 2 out here, and I kind of have it off to the side here. It's a little off the screen. It says square roots, we usually don't write the index. If there is no index on a radical, we just assume it's square root. Okay, but if we use any of the other ones, like for example, if I were to say the cube root of 8, okay, what this means is what number, when I cube it, will give me back an 8, and that would be the answer to the problem. So in this case, the answer to that is 2 cubed would give me back 8, so the cube root of 8 is 2. It's the radical symbol is always just asking the question, what number, when I raise it to this particular power, gives me back what's underneath the radical symbol. So the thing that's going to change now is we've only been focusing on what number, when you square it, gives me the radicand. Now we're expanding on that, and we're saying what number, when I raise it to the third power, gives me the radicand, or the fourth power, or the fifth power. So we're going to be focusing just on some more, we're going to expand this idea of radicals to include more things. Okay, so before we actually get into the details of that, let's talk about just some of the properties of radicals that you've used. So we're going to do a few of them here. Just focusing mainly on the first one in this list. And then in the second video, in the next video, we're going to take a look at some of the other properties and operations that happen. Okay, so here are the properties of radicals. Okay, I'm sorry, here's what's true for a radical to be simplified, and we're going to use properties to fix that. So if a radical is in simplest form, 3 things have to be true. Okay? There are no factors of the radicand that can be simplified, right? So when we did square roots, we actually said there are no perfect squares under the radical. And that's what the first one used to say. And so we're changing that idea up a little bit. We're actually saying when I split the radicand into factors, then none of those factors can be simplified using the radical with the index provided, right? So we have to be a little bit more general now. Okay, the other two are staying the same. So the second one says no fractions under the radical. Very easy to fix. We'll talk about that one later. And there are no radicals in the denominator of a fraction. That's what we called taking the rationalizing the denominator. If I ask you to rationalize the denominator, that is getting the denominator to be something that does not have a radical in it. Okay, so let's start off simple. Okay, that first step in simplifying a radical expression said that we're not allowed to have any factors of the radicand that can be simplified. So let's see what that means in an actual problem. So in this problem, I'm asking you to simplify the square root of 27. And this is something that you should know if we're talking about some of these higher order ones like cubes. So in this case, what it means is I'm going to factor 27. And because this is a square root, I'm going to try to factor it so one of the factors is a perfect square. So in this case, we know this one. We've done the square root of 9 and the square root of 3. 9 times 3 gives me back 27. So I'm looking at one of the factors of 27 and saying, I can take the square root of 9. That's 3. So I'm going to say this turns into 3 times the square root of 3. Okay? And so if you want to see a second example, this one has a little bit of algebra in it, so we have to expand this idea to problems that deal with, some variables and some exponents, but that's not a big deal. Okay, so the square root of 48 breaks up. It has a factor of 16 in it. It's the square root of 16 and the square root of 3. Okay, and now I need to think about these variables. Can I square root a squared? Right, that's a factor here. And the answer to this one is yes, right? If I square root a squared, or in fact, if I squared any even exponent, right, I'm just going to be able to cut that value in half. And again, this is something that we've seen before. The square root of a squared is a to the first power. If there was the square root of a to the 10th underneath this radical, we would just cut 10 in half, and we would say the answer is a to the 5th, right? b to the 7th, though, I would say b to the 7th, I can't cut that one in half. So I'm going to break that up a little bit, and I'm going to put 6 of the b's underneath a radical, and then I'm going to leave the 7th one under its own radical. So in this case, this one simplifies, and I'm going to say the square root of 16 I can simplify, that is 4. The square root of a squared, I can simplify that, that's a. The square root of b to the 6th, I can simplify that, that is b, and the 6 will be cut in half and give me a 3. The 2 is also cut in half, and there's technically a 1 there, but we don't usually write a to the first, but we'll put it there just for clarity. Okay, so I'm looking at what I haven't simplified. I did not square root the 3, and I did not square root the b. Those items are going to go back underneath the radical and be multiplied together. And I'm going to say this is the simplified version of our expression. Right? So we're taking this idea of simplifying radicals. We can apply it to variables and exponents as well. All of our even exponents can be simplified just by cutting them in half. If they're odd, like b to the 7th, we're just going to break off the odd b and at least cut the 6 in half, right? We can cut most of it in half, okay? So we're going to skip the try, and we're going to get right into, well, what happens if now I change the index? How does this idea of simplifying change if now I'm trying to simplify a cube root? Okay, so we're going to look at this problem and say, all right, now the question is, can I take the cube root of 8? Okay, and so I have a handy little guide over here. We need to start thinking not just about the perfect squares, right? We know to look for things like 9 and 16 and 25 and 36 because those things are perfect squares. That is 3 squared and 4 squared and 5 squared and 6 squared, right? But now we're not dealing with square roots anymore. Because this is an index of 3, now I'm dealing with cube roots. So if I'm going to be able to simplify something underneath a cube root, it needs to come from a perfect cube. And so this list that I have over here in the box is the list of the first 12 perfect cubes. So 1 is 1 times 1 times 1. And 8 is 2 times 2 times 2. And 27 is 3 times 3 times 3. So this is another special list, just like our list of perfect squares. Whenever I'm dealing with a radical that has an index of 3, which we call those cube roots, I'm going to look for this list of numbers because they're going to be the ones that simplify. In this case, the cube root of 8, I'm going to look at this and say, the cube root of 8 would be what number cubed gives me 8? And I can look at this and say, 2. The answer here is just 2, right? 2 times 2 times 2 gives me 8. So that's going to be the cube root of 8. When I start looking at like the cube root of 54, though, I'm going to look at my list and say, wait a second, I don't see that on my list. So I'm going to do the same thing that we just did with our perfect squares. I'm going to say, can I factor 54 so that one of the factors of 54 is on this list? And the answer is yes. This is 27 times 2. 27 times 2 gives me 54. So I'm going to turn this into the cube root of 27 at times the cube root of 2. Right? And the reason that I did that is because now I can look at my list and say, can I take the cube root of 27? The answer is yes, I can. The cube root of 27 is 3 because 3 times 3 times 3 gives me a 27 back. So I can at least simplify one of the factors, and then the other one is going to stay underneath the cube root symbol, and I would say, sorry, that's 2, okay? And I would say that is now my simplified expression. So if you remember, what we said was, if this is going to be a simplified radical, that we have to factor the expression and then try to simplify the factors. And in this case, I could simplify the cube root of 27, so I did that. Okay, so just one last example of cubes, right? And we're going to use this one just because this is the first time we're seeing a negative underneath a radical that I'm going to claim is something that you can simplify, right? So as an example of something, when we were talking about square roots, we said if I gave you the square root of -9, we couldn't simplify that directly, and we had to involve complex numbers and I and all of those slightly more advanced concepts. I'm claiming for cube roots, and in fact all of the odd index numbers, that we can cube root or root all of those negative ones, and here's why. Okay, again, I'm asking the question, is there a value that when I multiply it by itself 3 times gives me -125? And if you take a look at my list here, positive 125 shows up on the list. So I'm kind of saying, all right, well, 5 to the third is 125. Well, I don't need 125. I need -125. And here's the reason that this works. Okay, if I change this on the left-hand side to being -5 to the third power, I'm going to say -5 times -5. Well, that's 25. 25 times another -5 is -125. So I can actually answer their question out. Is there a number that I can multiply by itself 3 times and end up with a negative answer? The answer in this case is yes. Okay, so I actually, for these odd index roots, okay, negative numbers are okay to be under the radical. So I'm going to say in this case the answer is -5, because -5 cubed gives me back 125.